So we left off saying we needed a new thermodynamic variable. That thermodynamic variable is Gibbs free energy. The second law tells us that reaction spontaneity is described by the sign of the change in the entropy of the universe for our reaction. So this really is what matters. For something to be spontaneous, it needs to cause a change in the entropy of the universe that is positive. Negative means it's not going to happen, right? That's a non-spontaneous process. And for the purpose of the chemical reaction, it doesn't happen. You're not going to turn those reactants into products. So this is really what we want to calculate. And so this number characterizes spontaneity. Is it positive or is it negative? We can break that up into, the reaction surroundings bit, because, you need to have a way to actually something tangible to calculate here. And we further take those and can kind of rewrite those. And we've seen it's based on the change in the entropy and the enthalpy of the reaction. And so while we may actually care about the delta S of the universe, we can't just directly look that up. We can't calculate it from just, some tables of information. We can calculate delta S of the reaction and delta H of the reaction from tables of information, reference information. And that's really useful. We also kind of want to continue this move. Universal perspectives are generally meaningless, whereas this sort of reaction-based perspective is something we want to continue on and kind of more focus on for describing spontaneity. To that end, we will define the Gibbs free energy. So Gibbs free energy is appropriately, the symbol is capital G. After Gibbs, Josiah Gibbs was one of the first real American physical chemists, real big importance in the history of chemistry being studied in this country. And so the units on Gibbs free energy are kilojoules or kilojoules per mole. So it has the same energy same units as energy. You'll note that's why it's in the name here. There's that word free, which we'll talk about, but Gibbs free energy is G. And Gibbs free energy describes spontaneity of processes under constant temperature and pressure. So the reason why this is still describing the same idea, but you'll remember spontaneity, second law of thermodynamics, delta S of the universe, that's always it. It does not matter if you're dealing what your conditions are. Spontaneous processes always correspond to an increase in the entropy of the universe. So Gibbs free energy does have these qualifications, constant temperature and pressure, but that just means you're in a lab, right? When you're doing lab work, you're under whatever the temperature of the air is, whatever the pressure of the air is. And so that's basically the chemically useful conditions. So that's why we can use Gibbs free energy. Gibbs free energy is composed of enthalpy and entropy. So the change in the Gibbs free energy of a reaction or of a process is equal to the change in enthalpy minus the temperature times the change in entropy. So it's the same ideas that we saw combined together previously. You'll note in this definition, we don't have like cis and surrounding designations. That's because they all describe the same thing. So if you were to put in the designations, they would all say system or surroundings. You could figure out delta G of surroundings. Don't really care that much about it, but you could. But it's all going to be delta G of the system is equal to delta H of the system minus T times delta S of the system. So Gibbs free energy is all about the spontaneity of a process. So how do we take it? How do we interpret a value to figure it out? So we're going to do some derivation. We're going to start with the definition of Gibbs free energy. Delta G is equal to delta H minus T delta S. And what we're going to do is we're going to do some algebra. We're going to divide by negative temperature. So that's all we're doing. That gets us a new version of our equation. Okay. Then we're going to make a specification. We're going to define everything as the system. Okay, so that's what's going on here. Then we're going to use the definition of delta S of surroundings that we looked at previously. So negative delta H of the system divided by temperature. That was the definition of the surroundings. And finally, we're going to just use the definition of the delta S of the universe, that systems plus surroundings. So we know that delta S universe positive means spontaneous. So delta G of your system that's negative corresponds to spontaneous processes. So it is an opposite of the sign that we're looking for. So again, if you want to know spontaneous, you just get the number and look at the sign of delta G. So any process that is spontaneous corresponds to a negative change in the Gibbs free energy of the system. But really one of the important things, the real motivation behind it here is instead of worrying about a property of the universe, we are looking at a property of just the system, which in this case would be a chemical reaction. What's the change in Gibbs free energy from reactants to products? And so when you have these constant temperature and constant pressure system conditions, if you know the sign of delta G, you know whether or not the reaction is spontaneous. Negative, reaction is spontaneous. Positive, reaction is not spontaneous. Those reactants are not all going to turn into products. Delta G is preferred because you're describing the reaction. You're describing the reaction itself. And so this is describing, what you're interested in knowing the spontaneity of. You can get some information out of it. We're going to see there's also some tools that we can use to kind of understand and how we can control reactions, how we could change spontaneity and cause something to occur. And that's all a big part of why we define delta G. And so, for example, in the previous when we were previously looking at spontaneity, boiling water at 25 degrees Celsius, we calculated delta H and delta S. We calculated them in the way to get delta S of the universe. We could take them and plug them into this equation. You literally just plug them in, the delta H, the delta S. You just multiply it out. You do want to be mindful. We're doing subtraction. One of the biggest issues is not making those units be the same. So generally, entropy is always in joules and enthalpy is always in kilojoules. You do that subtraction, and you get that delta G naught is 8.6 kilojoules per mole for boiling water at 25 degrees Celsius. That's a positive number, so boiling water is not spontaneous. We can use the same inputs. We use the exact same tabulated information, and we get the same answer, being that it's not spontaneous. We do get this number 8.6, which we will see can be used and implies some things, but the sign describes whether or not it's spontaneous. We got a positive number here, as expected, because water does not boil at 25 degrees Celsius. Also consistent with that, we got a negative delta S universe. So what is delta G? Right? We know the sign tells you spontaneity. And what delta G quantifies is the maximum work that can be harnessed from a process. So basically what this means is if you want to get useful energy, work being useful energy, you're making something move, it has to be spontaneous, which makes sense. And the negative sign is work coming out. And so that's why delta G negative corresponds to a spontaneous process. That doesn't mean you will get that much work out of it, just that you can get that much work. And so this also kind of fits into why we have, and where the free comes from free energy, but why we also have kind of the enthalpy and the entropy component. So basically the enthalpy we generally think about as heat or energy, and that would be kind of the amount of energy change, say, from reactants to products. But whenever you have a process, if there's heat involved and energy involved, some of it always gets lost towards modifying entropy, increasing that disorder. That's not useful energy. That's not work you can use. And so that's why there's these two components. There's this kind of inherent energy in the enthalpy part, but there's also this kind of sink that you have to lose some energy towards the kind of randomness of increasing that sort of loss of heat, loss of matter, loss of something, kind of sacrificed to the entropy. And so when delta G is negative, it's a spontaneous process. It's gonna happen, and that system can put out work. When you do that chemical reaction, you can make something happen, right? And the amount of something you can happen is equal to the actual value of delta G. We're not gonna go too much into that, but that is what, kind of comes out of it. Or you can use it to kind of look at efficiency and kind of outputs and stuff like that. So delta G greater than 0 means it's not a spontaneous process because energy needs to be put in to make the change happen. That's what a non-spontaneous process is. The process won't happen without input work. And importantly, the delta G positive is actually a number we see and use more often because that tells you how much energy you need to put in. Right? If it's, in the previous boiling water is 8.6 kilojoules per mole. If you do 8.6 kilojoules per mole of work on water, you can make it boil at 25 degrees Celsius, but you got to put in that work. It's important to note that is different than just heating it up where you're changing the temperature. It does have to be in the form of work. So that does kind of complicate it, but it does tell you at least the kind of the threshold. You need this much work to get this non-spontaneous process to happen. It won't happen without you putting in work. Energy as work. Okay, first video down. No participation questions so far. Looking for 1031, October 31st. We got the week 10 homework due Saturday, covering all of chapter 16, and then the post-lab for acid-base titration is due on Sunday. Otherwise, welcome to the second half of chapter 16. I will see you in the next video.